Hey, this is lesson 2.2. Building bird feeders is for the birds. And this is all about determining equivalent ratios. Our learning goal for today in this lesson is going to be to determine if the points on a graph are equivalent ratios. And hopefully at this point you know what equivalent ratios are, and you'll be able to answer the questions accordingly. So woodworkers create and repair all sorts of items and structures that are made primarily of wood. If the item is made of wood, they probably know how to sand it, glue it, build it, stain it. Woodworkers use tools such as jigsaws, levels, T-squares, and chisels. Woodworkers can create tables and chairs, chess sets, birdhouses, and feeders, and well, just about anything that's made of wood. They are the pros of pine, wizards of walnut, and champions of chestnuts, and maestros of mahogany. That one's for you, mahogany. How do you think the woodworkers might use equivalent ratios? Do you think woodworkers would work together to complete projects? Okay, so you have some space here. I'd like you to think about that question. Um, how do you think woodworkers might use equivalent ratios? And then, do you think woodworkers work together to complete projects? I mean, the second one is obvious. Woodworkers do work together, or they can, but they don't have to. But I want you to use this space in your book to write an answer to that. Problem 1 is called building feeders. Bob and his little brother Jake want to build bird feeders to sell at a local farm or farmer's market. They have enough money to buy materials to build 10 bird feeders. If Bob builds 5 bird feeders, how many will Jake need to build? Well, I hope that you're thinking out of 10 bird feeders, if Bob builds 5 of them, Jake will need to build 5 as well. So Jake will build 5 bird feeders. It says complete the table by listing all the possible ways in which they can divide up the work. So this is the number on the left side, or left column is the number which represents X, because remember, the first column is always representative of X, and then the second column is representative of Y, so that if you have to take a data set and convert it into a graph, then you always know what X is and what Y is. So if Bob builds all 10 bird feeders, Jake would have none left to build. If Bob built 9, Jake would build 1. If Bob built 8, then Jake would have to build 2, because again, we would like all of these rows to add up to 10 total, because it says 10 up top. So continuing on, if Bob built 7, Jake would build 3, and so on. And you can see the pattern as follows. I didn't put the rest of this table in the PowerPoint, so I want you to go ahead and complete the table, and then we will move on. So the next part of this, part 3, complete the graph by plotting the quantities from the table you completed. So this is pretty straightforward. We're taking the table that we just created, and we are going to plot the points of data. So going back to this, don't mind this. Going back to this, we're looking at each one of these like an ordered pair. Okay, so again, the X is the first column, and the Y is the second column. So our first point is going to be 10, 0. Our second point is going to be 9, 1. And our third point is going to be 8, 2. So I'm going to do those first 3 points with you, and then I'm going to ask you to complete. If you did 2.1, this should be pretty easy for you. So our first point is up to 10, and then it says 10, 0. So I just plant that point right on the graph at the 0 line for the X. The next point was 9, 1. So I'm going to go over. Okay, so scratch that. Again, if the first column was X and the second column was Y, I just plotted those backwards. So what you should have done instead of this point, now this point is going to end up being on our graph, but it's our very last point, which is 0, 10, meaning I'm not going anywhere on the X, but I'm going to go up to 10. It's the very last point in your table. This point is actually over 10, and then you don't go anywhere on that y-axis. The second point is 9 ones. We're going to go over to 9. We're going to go up to 1, which is here. Okay. The third point, we've gotten those two taken care of. We have 8, 2. So we're going to go over to 8, and we're going to go up to 2, which is here. I want you to continue those points, so pause the video, see if you've got them done correctly. So this is the way your points should look if they are all graphed correctly. The next part says to draw a line connecting the points on this graph. So we're going to start here. We're going to draw a line. I can't use a ruler on this computer, so I'm going to try my very best to make it as straight of a line as I possibly can without a ruler. You should be using a ruler when you're connecting these points. The next part, describe the line you drew. Do all points on the line make sense in terms of the problem situation? So if you remember back a couple lessons ago, we talked about whether it makes sense to connect the points on the line or not. So if you look at what's on our X here, we have bird feeders, the number of bird feeders. On the Y is the same thing, the Bob's number of bird feeders. So would it make sense to connect these points on the graph? I'm going to let you think about it for a second. So now that you had a chance to think about it, I hope you're thinking in your mind that it does not make sense to connect these points. The reason why it does not make sense is because Bob nor Jake would build half or a fourth or 3/4 or 2/3 of a bird feeder. And when you connect these points on that line, you're saying that any fractional part of a bird feeder is appropriate. And that is not the case, because I don't think anybody would want to buy a bird feeder from Jake that was only 3/4 of the way done. So it doesn't make sense for you to connect the points, because it's indicating that it's continuous data. When this is not continuous, it is discrete. There are no fractional parts nor decimal parts to this data. So it says describe the lines. We have a straight line. Then it says, does it make sense? Does each point on here make sense? Well, the ones that we plotted make sense. But again, when you connect them, you're saying all fractional parts in between those two whole points make sense as well. And in this case, they don't. So no, not all points make sense. Because we don't need to include fractional parts. The last question says, describe how the number of bird feeders built by Bob affects the number Jake builds. So I want you to think about it for a second. So I'm hoping you're thinking something like this. The total number we know must be 10, and they're sharing this workload. So the more Bob builds, the more bird feeders Bob builds, the fewer Jake has to build. And then the fewer that Bob builds, the more Jake has to build, because again, it's kind of, they share this responsibility. So if I'm Bob and I only do 3, that means Jake has to do 7, and vice versa. The next question asks, what is the ratio of bird feeders that Bob needs to build to the number that Jake builds? Explain your reasoning. Well, in this case, there is no one ratio because the ratio changes for each number of bird feeders each person builds. So for instance, like if I build 3, that means Jake has to build 7. But if I build 4, Jake builds 6. So it's going to change every single time. There's no equivalence within the numbers that I build or Bob builds versus Jake builds. And then number 8 says, Dontrell claims that the number of bird feeders Bob builds directly varies with the number of bird feeders Jake builds. Do you agree with Dontrell's claim? Explain your reasoning. So I want you to think about it for a few seconds, come up with what you think the answer might be, and then come back and check yourself. Okay, so no, Dontrell is wrong, in fact. Even though the quantities in the graph appear to make a line, the points do not pass through the origin, which is 0, 0 on your graph. If they don't pass through the origin, then there is no relationship between the two quantities, and they don't vary directly. I mean, there's a relationship, I shouldn't say that, but the quantities do not vary directly. Varying areas of rectangles, but do they directly vary? Vanessa was given a math problem to determine how many different rectangles can be constructed with an area of 12 square inches. Vanessa thinks that there are only 2, one with a width of 2 inches and a length of 6 inches, and another with a width of 3 inches and a length of 4 inches. Is she correct? Explain your reasoning. I think you should be able to work through this one, so I'll give you a second to come up with what you think your answer is, and then come back and check yourself. So go ahead and check yourself. There are many, many more rectangles with an area of 12 square inches. An example would be a 1 inch by a 12-inch rectangle. Complete the table by determining the unknown value. So if we had 1 here, we just talked about this as our example, then we would have to have 12, because 1 times 12 equals 12. Again, the point of this table is to multiply the two numbers together to get a total of 12. So 2 was the length, then 6 would have to be the width, because 6 times 2 is 12. If 4 is the width, then 3 would have to be the length, because 4 times 3 is 12. If 1.5 were the width, then what do you think the length would have to be? Well, in order to determine that, we would have to say 12 divided by 1.5. That would give you 8. I'm going to let you finish the table, come back and check yourself. So here are the remaining values in the table. I hope you got these. Let's move on. We are now going to graph the data. So again, going back here, this is going to be our x, because x is always the left or the first column, and this is going to represent our y, because the right side is always representative of y. So that is why they put width here, because it represents x, and length here, which represents y. So our first point would be 1 up to 12. So it is right here. Now, some of these are going to be easier to plot than others, because obviously we have some fractional parts here. The second point would be 6, 2. So over to 6 up to 2. Whoop. Mine is just a little bit larger than it should be. You can fix that on yours. The next point is 4, 3. So we're going over to 4. We're going to go up to 3, which is here. Again, mine's a little bit bigger, but it's hard to use this to draw these points. The next one is 1.5 and then 8. So here's 1. Here's halfway, so that's 1.5. Here's up to 8, which is here. Then we have 1 1/3, which is 1.3. So that's going to be a little less than 1.5, which is this. So we're going to go 1.3, and that's going to go up to 9. So it's going to be like right in here somewhere. And then we have 20, and that's 0.8. So over to 20. 0.8, well, we know 1 is here, so it's going to be a little less than that. That's here. And then we have 16 and then 3/4. So over to 16 up to 3/4, which is going to be just a little bit. That was actually a little bit too high because it's not all the way on that one, or it shouldn't be. It should be right around the same as this one, just a little bit lower. So my point is off. But again, this is very difficult to do with this technology that I have. So the next point, or the next question just says to draw a line. So your line should look something like this. And this is gonna, if I continued this, it would just go straight up. Okay. Again, it is very difficult to do this on this program. So it says describe the line you drew. Do all the points on your line make sense in terms of the problem situation? So I want you to think about this, and I want you to answer question 5 and come back and check yourself. Okay, so I'm hoping that you just explained that the line was curved, and that yes, all the points make sense because the length or width of a rectangle can have fractional parts. It makes sense for the length to be 1.5 and the width to be the width to be 1.5 and the length to be 8, or the width to be 1 1/3 and the length to be 9. Those are all fractional parts. And again, when you connect the points on a graph, that just means that all of the fractional parts in between the points that we plotted all make sense for the situation. And in this situation, it does make sense because a rectangle can have a length or width with fractional parts. Okay, describe how the width of the rectangle affects the length of the rectangle. Well, we all should know that with the area of a rectangle, we should know that that is length times width. So the product of the width and length is equal to 12. And then it says, what is the ratio of width to length of the rectangles? Well, I hope you're thinking that there is no one ratio because the ratio changes for each value. Go ahead and write that down if you haven't already, and we're going to move on to problem 3. Problem 3 says bamboo can grow, grow, grow. One species of bamboo can grow at an average rate of 60 centimeters per day. Assuming that the bamboo plant maintains the average rate of growth per day, how tall will the bamboo plant be if it grows for 10 days? Well, if it's 60 centimeters per day, and then times 10 days, that's going to give us a total of 600 centimeters. I'm going to let you finish the other two and then come back and check yourself. So I'm hoping that you figured out each time we just multiplied, because it's 60 centimeters per day, we're taking 60 times 10 days, 60 times 30 days, and 60 times a half a day, which gives you the according products. Assuming that a bamboo plant maintains the average rate of growth over time, how long has it been growing if it's 20 centimeters tall? So we're going to look at these problems a little bit differently. I want you to think about it, come up with one answer for A, and then come back. So I hope you've realized that instead of multiplying by 60, we're going to divide by 60. So 20 centimeters divided by 60 centimeters gives me 1/3 days, because if I wrote it in fraction form, it would scale down to 1/3, which is 1/3 days. And then for this one, we would have we would have 200 divided by 60, which would give me 3 1/3 days. So you're either going to scale up or scale down based on the information that they give you. Number 3, complete the table using the given growth rate of bamboo plants. So if we have 10 days, we've already figured out, this is from the first part, that it would be 600. If we have 30 days, it's going to be 1800. If we have half a day, it's going to be 30. From here, if it was 20, then it's 1/3 of a day, and then this one was 3 1/3. I want you to go ahead and try to graph this, come back and check yourself. Okay, so check yourself. Again, I'm really sorry that this is coming out that way. It's just very, very hard for me to not flip my pen. Again, you should be using your ruler to connect these points because this line should be a very, very, very straight line. Um, the next part says to describe the line you drew. So you would say that this is a straight line that increases from the origin, okay? So this line starts at 0, 0 because when you have a seed that you plant in the ground, it's 0 inches tall to start off with, like above the ground. So when you plant a seed, it is 0 on that soil. You don't have anything to measure yet. So it's 0, 0. That's why it makes sense. In this case, it asks about whether it makes sense to um, connect the points in the line. In this problem, it does make sense because it does make sense to have a fraction of a centimeter in height. Okay, and then as the plant grows, it's not going to stop growing until it's all the way finished growing. If it continues at the same rate, then it's going to have little bits every day, and little bits, as we know, can be fractions of 1. So yes, it does make sense. I'm not going to write out all these answers to this. I'm talking you through it. I need you to write the answers out on your own. The next, number 7, says describe how the time affects the height of the bamboo plant. And so this one is each day the plant grows 60 centimeters. So that is how the height affects, how the time affects the height of the plant. Number 8, what is the rate of the height of bamboo plant to the time? And you should know that we've been writing out our rate, so 60 centimeters to 1 day. Now this one actually, it makes sense to write a ratio because this is the rate that continues. It doesn't change every single time. So that's what we call the constant of proportionality. So it says go back and examine all the graphs in this lesson, and I want you to answer the talk questions that come up next, and then check yourself. And then you can move on to the skills practice.